Hello, everybody. Welcome. Thank you so much for having me, NDC Sydney. I'm really excited to be here. And I am going to talk to you today about this thing right here. This is a flexible LED array, which is built into a mask, which live captions what I'm saying as I'm saying it. But before we dive into the tech, let me introduce myself. I'm Jo Franchetti. I am a developer advocate at Ably, and Ably is an edge messaging platform which helps developers like yourselves to build live and collaborative experiences. We have an evolving suite of SDKs and APIs that give you the freedom and flexibility to power collaborative apps like chat, to do order delivery tracking, to make multiplayer games, to do document collaboration, and to connect millions of devices around the world together. And I'm primarily a web developer, but I do dabble in IoT as well, as you can see. My first ever project, I put LEDs in my wedding dress so that my friends could tweet a color at the dress and it would change to that color, like that scene in Sleeping Beauty where the two fairies are fighting for pink and blue, pink and blue. I also made a Christmas jumper that shows a different emoji depending on what Christmas music is playing. And I have to admit that I have a personal desire to see more products like this one in particular on the market. And the reason for that desire is because of this woman here. This is my mother, Mama Franchetti. And she's a smiley and sociable and quick-witted woman who loves to have a natter with her friends. But she's also been steadily losing her hearing over the last few years. She went to too many loud rock concerts when she was young. And losing her hearing has been an incredibly isolating experience for her, as I'm sure it is for many people. She relies really heavily on lip reading and clear enunciation. And you know what makes lip reading and clear enunciation really difficult? When people are wearing a mask. And if she was struggling to join in conversation before, when Corona hit and everybody was wearing masks, as they rightfully should, it just made it so much more difficult for her to engage with people. She couldn't socialize with her friends, and she couldn't understand people even in day-to-day moments like in shops. And people have a tendency to become rude or to brush people off when they're asked to repeat themselves. So she gets really self-conscious and she tries to style out not having heard what you said, and it makes conversation really difficult. So I have a couple of asks for you all throughout this talk, and my first ask is this. If somebody ever asks you to repeat yourself, please don't just say, oh, don't worry about it, because the person on the other side quite often is only hearing half of what you're saying, and they're not actually able to engage with you. So as we traversed her hearing loss, one thing really struck me, and that's that we, as developers, aren't really doing a brilliant job at making assistive technology. Now, my mum has a cochlear implant, which is a really cool piece of technology. It's a wire that they put basically inside your cochlea that does your hearing for you, and it basically beams sound directly into her brain. Like, my mum is a cyborg. It's super cool. And the device has a little battery that clips over her ear, and the processor is actually underneath her skin next to her skull. And she can stream sounds from like her devices directly into her head, which is like super cool. But for some reason, this particular device, and there's two main brands of devices out there, this particular one only has an iPhone app. It doesn't have an Android app. My mother's been an Android user her whole life. And, you know, she's fairly tech savvy, but not the most. So learning an entire new operating system just so she could hear was a real frustration for her. Not only that, but a few years ago, iOS released an update that had nothing to do with the cochlear implant, just a normal update to the operating system. But everyone who had this particular implant had screaming streamed directly into their head for a couple of hours before they turned it off. Which just, it's not good enough. We tend to want to work on, you know, the new shiny things, the sexy things, and assistive technology and aging technology. They're not the sexy things. They don't get the attention that the glamorous software engineering jobs get. But in, 50 years, maybe less than that for some of us, we're going to be the ones who need this technology. So we really need to be the ones who are working on it. And goodness, we can do better than streaming screaming noises into people's heads. So my second ask is this: let's put some effort into building assistive technology to consider our fellow humans on a day-to-day basis. And if you can't consider your fellow human, maybe consider yourself in 50 years' time. So story time is almost over, I promise, but I was worried for my mum. She got even more isolated than the rest of us did during lockdown. And the assistive technologies that ran on her phone meant that she had to be looking down at her phone the entire time that she was trying to converse with someone so she could read the live captions. And that often meant that people thought that she had disengaged from the conversation. They thought she was just checking her phone. And so people had a tendency to ignore her or to shut down mid-conversation. And people also get a little bit concerned if they think that you're recording their conversation. And I'm a developer, we're all developers, we like to fix problems, that's what we do. And I thought I should be able to fix this problem for her, and inspiration struck me in the weirdest of places. If you're ever in London, do consider visiting this place here. This is Cyberdog, it's a shop in Camden, and they sell basically rave clothing, so lots of clothing with lights in it. And one of the things that they were selling was this thing, which is a mask which has LEDs in it. And it had a really nice high resolution, and it could do all these sort of fun animations. And I bought one immediately thinking, this is awesome, what if I could put text on here? I could signal what I was saying so that my mum could look at my face while she was speaking to me. She'd basically be able to look me in the eye like we were having a normal conversation. But the display that came in this mask, it had its own built-in processor with its own app that was written in Chinese and obfuscated and clearly full of all sorts of awfulness. And I couldn't work out how to reverse engineer it. I tried Bluetooth sniffing the packets that were sent to it. Managed to get to the point where we could update 1 pixel at a time on the mask, but it just wasn't fast enough to run text. So not wanting to be beaten, I thought, well, fine, I can make one myself. So if we're going to build an LED display ourselves, we need to, if we're going to build a live captioning mask, we need to break it down into its component pieces. So the first thing we're going to need is a flexible LED array of some kind, built with something called addressable LEDs. And when we talk about addressable LEDs, what we mean is that each LED has its own numeric address so that we can send data to each particular LED in the array. Then we need a way to control that display, so a small processor board of some kind, and we will need also some kind of small battery to power the board and the display. And it all needs to be small enough that it can A, fit in a mask, and B, maybe fit in your pocket. And then finally, we need a microphone which is going to pick up the speech, and we need some way to process that speech and turn it into text. So let's start with the LED array. This is just a flexible array of 28 by 8 NeoPixels. NeoPixel is the name of the brand of the addressable LEDs that I used. There's a larger version of it here if you want to come up later and have a look at it. It's nice and flexible. And we can put small holes in between the LEDs to allow for breathability. And it's powered by a small microprocessor. So this is the microprocessor in question. It's just about small enough to fit into a mask. It's 5 centimeters by 2 centimeters, and it can be powered by a USB battery, so something about this size, which is nice and easy to put in your pocket. It has Wi-Fi on the board, so you can see there the Wi-Fi antenna down the bottom. And I could have got a tiny little microphone and soldered it onto the board, but honestly, doing audio streaming plus controlling the LED array is perhaps a little bit too much for this tiny board. But the board does have Wi-Fi, as I mentioned, and we all carry microphones around in our pockets with us every day. So why not outsource the microphone and also the audio processing to this much more powerful device that we already have on us? I could make a web app to do the processing and send the return text back to the board to display. So let's talk about the web app. It uses the microphone in the phone In the web, we've had the ability to use the microphone for a long time. To translate the speech that is picked up by the microphone, I'm using Azure Cognitive Services. If you've not used Cognitive Services before, it's a whole suite of APIs that allow you to add AI capabilities into your apps. And one of these capabilities is speech to text. So the web app itself that I built is just a Node app. It uses the Azure Cognitive Services speech SDK. It uses a driver for the LED display that I built, which I will talk about in a bit. And it also uses a specific transport protocol to send the data from the web app to the microprocessor. And the app itself has some very basic UI. It looks like this. So what we have here is we have a button to start listening, to start using the microphone on the phone. And then it will start streaming the microphone input to Azure Cognitive Services, which will return some text, which will be shown in that white box there that you can't quite see. And then I also have on this app a visual representation of the LED array, which is really helpful for debugging, and also some color settings and some speed settings. So I can change the speed at which this scrolls, and I can change the color as well, just for funsies. So let's start by hooking up the Start Listening button and get it talking to Azure Cognitive Services. So here, what I've done is I've wrapped the Cognitive Services speech SDK with this code here. So under the hood, Azure Cognitive Services is using get user media, which is how we get the microphone. It's been in browsers for ages, as I mentioned. It prompts the user for permission to use the microphone, and then it'll stream data from their media devices, and it'll use something called stream speech from browser, which is a function that comes in the Azure Cognitive Services speech SDK, which you can see there. So what that does is it uses the microphone input along with an authorization token, which will authenticate with Azure, and it'll initialize a speech recognizer. And the speech recognizer is what is actually going to perform the speech recognition. So it returns an object. So we send it the stream of sound that we're getting, and it returns an object which contains the text of what has been said. And then in the main app, I wrapped the Azure Cognitive Services speech SDK with a class, which allows us to provide it an API key. And then I register this on text recognized. And this callback subsequently calls the matrix LED driver. And that will then be able to power the lights on the board. So now let's talk about how we actually communicate with the board itself. How do we get, now we've got this text transcription which has come through, we've got this array of words. How do we get this transcription from the phone to the microprocessor? We need some kind of messaging protocol, and I use MQTT. And MQTT is great for IoT projects. It's lightweight, it's publish, subscribe, it's optimized for high latency, unreliable networks. If you think about it, if you're walking around town with a mask on, you're unlikely to have much battery power, you're unlikely to have an excellent connection. We might even be on 3G, so we need something optimized for high latency and unreliable networks. And in order to use MQTT, we need some kind of broker to do that. And this is just a service that is responsible for dispatching the messages and making sure that the sender is sending them to the correct recipients. So in this case, the web app is the sender and the microcontroller is the receiver. And I use the Ably MQTT broker because I work at Ably, and it's super cool. It sends messages. So because I'm building a web app, I'm able to use the Ably JavaScript SDK, which is just a pub/sub SDK, and it sends out the messages over WebSockets, which we would expect in the web, but it also automatically sends them out over MQTT, so I don't need to do any extra configuration here. And as I mentioned, the microprocessor is really small, which means it has limited power and limited memory, which means that the code that runs on it needs to be as efficient as possible. So we really want to avoid doing complicated text parsing or other similarly memory-intensive tasks. And parsing and splitting strings is especially costly, and it involves quite large buffers, which is not really optimal for the tiny little processor that we've got. Just in case you want an example, it's that big. And so we're going to try and optimize the amount of memory that we're using on the board by not parsing the messages. So to solve this problem, we're going to use a binary message format to encode the data that we send to the hardware. So the browser is going to write specifically coded messages to send the strings to the device over MQTT. So if we take a look at an example command, most things that we write to send data would probably use JSON to serialize the messages. But in this app, instead, we're going to use this special binary format. So if we take an example of a message that might look like this, where we've got a line of text, we have a mode, so that's saying how do we want this to display on the mask. We have a scroll speed, so how fast do we want it to scroll, and we have a color as well. So if we're going to encode it, let's have a look at how we might do that. So we're going to pack it down into raw bytes and then use control codes from the ASCII standard to provide some header information in the messages. And because the message is a raw byte stream, it means we don't need to do parsing on the hardware. We can just loop over each byte individually and run different processes depending on which byte is being looped over at the time. And this is really cool. It takes all of the complexity away from the microprocessor and moves it into the JavaScript in the web app on the device, which has much more processor power. And it's much more easy to debug and test in the web than it is to debug and test on the device. So if we have a look at this table here, a byte at offset 8 would represent a single character, but the parser on the hardware is looking out for the STX and the ETX, so the start of text and the end of text markers. So what this means is we can send any number of ASCII characters to form full sentences of a message in between the STX and the ETX. So that's how we're sending full messages with strings of text in them. So next, let's have a look at hooking up the speech recognition. So earlier on, we registered a callback to onTextRecognized, and we called the matrix LED driver. What we didn't look at is how we create a connection between the browser and the LED driver using Ably as the broker. So there's a few things that are going on in this code sample. First of all, we're making an instance of the Ably JavaScript SDK. Then we're newing up an instance of the remote matrix LED driver class, which is the thing that actually drives the LED display. And it takes a display config, which changes how we encode the pixel data. And it needs a device adapter, which is the implementation of the encoding protocol that I just described earlier. So this is the Arduino device adapter, and it implements the binary protocol that we just talked about. And it requires a transport. So in this case, this is a wrapper for the Ably JavaScript SDK, which is how we're going to send the data. The data is sent out, as I mentioned, over WebSockets by the Ably JavaScript SDK, but also sent out over MQTT automatically. And this is super cool. It means that not everybody's going to have one of these LED masks with them in their pocket, but it means we can still do that speech to text in the browser. If somebody needs it, we can still do the live captions directly into the browser over WebSockets, but we have the option for connecting IoT devices. And that was a lot of data that I just dumped on you. But what that means is that we can call the functions available on the Matrix driver SDK, and it knows how to convert pixel locations to from our 8x28 array into absolute numbers that the NeoPixel hardware understands, so our address for each LED on that strip. It knows how to encode those numbers into a wire format using our device adapter, and it knows how to transmit the data over MQTT. So if we were to visualize the entire system, it would look like this. So we now have a way to send nice compact messages. Let's take a look at the display driver itself and how it actually reads those messages. So the LED driver, as I mentioned, has a whole load of different API calls, and this is because it was built across multiple projects that I've made. So when I mentioned I made the Christmas jumper, that was an array of 16 by 16 LEDs. This one is 28 by 8, so I needed a driver that understood all different sizes of displays. So it has a few different calls, as I mentioned. It can set a single pixel with an optional color, either in hex or RGB. I can also set single pixels where the Y coordinate is optional, and this is really useful if we've just got a single strip LED array. I can also set the entire display at once using this nice kind of visual coordinate. I can even send the entire images to the display, which is how the Christmas jumper worked, but the images have to match the resolution of the display. So in this case, they were 16 by 16 pixel images. But for the mask, we need to show text. And not only that, we need to show scrolling text. So we have the option to send text and also to send text with a color and an optional scroll speed. So let's talk about how that was made. So the first thing that I did was I designed this pixel font. It's got a whole load of alphanumeric characters and symbols, the ones that I use in speech every day. So you'll notice there aren't many accented characters here. And I need to convert from this pixel array into an array of binary values. This is just a sort of guesstimate of the characters that I'd need most, and I converted each of them into an array of pixels. So let's talk about how that might look. So if we take the letter N, for example, represented visually, it would look like this. We give a value to each of the pixels to make up the N. Then it would look like this. So 0 is off and 1 is on. And if we then change that to an array that we're used to seeing, it would look like this. And if we put that all on one line, this is the array that represents the letter N in binary. So what we've done here is we've encoded this 4 by 8 block into an array of bytes, which is super cool. And instead of encoding the entire alphabet by hand, which would have taken a very long time, luckily there's a library called GIMP which can actually do this for us. So I gave it the font sheet, which was just a PNG of black and white pixels, and it was able to convert it into an array of each supported character. So if you imagine this is one long line, I've taken some stylistic liberties here for slide design, but if you imagine all of this text on one long line, you may have noticed that some of the characters are different widths. So some of them are wider than others. This was a stylistic choice because I personally think that it's a little more legible than a monospace font. I think it looks nicer. But what this means is that not only will we need an array of each pixel for each letter, but we will need an array of indexes which tell us where each letter begins, so that we know where to start reading from. But that's it, that's all we need. These 2 byte arrays are small enough to be embedded on the microcontroller, and we have our entire font data. Then we can write code in C, C++, which is the language that the processor uses to show the letters on the display. So instead of computing each individual pixel position in the browser app and sending them one by one, the microcontroller can actually handle that translation itself, which saves us a lot of data over MQTT. We want to be sending messages that are as small as possible. So cool, we have a font. Now we need to work out how to display that font on the array, which, if you've ever done any work with hardware, like the whole point of this talk is that I want to sort of demystify working with hardware, but if you ever have worked with hardware, you know that it's never as simple as you want it to be. And the first problem that I ran across was that there are multiple different ways that LED arrays can be wired up. So LED displays like this one that I have here are, as I mentioned, made up of addressable RGB LEDs, which means that each pixel in the strip has a number assigned to it, but there's different ways that they can be wired up. So it could be wired up in reading order, like in illustration number 1. It could be wired up in what I've affectionately termed snake mode, which is how I usually wire things up, because it means I need fewer wires, because the jump is much smaller going from one row to another than one row all the way back. So it could be snaking horizontally. It could also be snaking vertically. I think this board here, yeah, this one snakes vertically, so up and down, which meant that I needed a way to tell the display how it was wired up. Not only that, but again, if you have a look on the back of this one here, I don't know if you can see it, but there's different points where we can put data in. So we need to not only tell it how it's wired up, but which end the data is going into, so that we know which side to start counting our addresses from. And that meant I needed to update the driver to accommodate all these different physical constraints. Most displays are wired up in this sort of snake mode. Obviously, it makes a lot more sense. But this variety in wiring patterns just caused a whole load of extra complication, which meant that I needed to translate from XY coordinates to an appropriate pixel ID. And so I needed to ensure that the JavaScript would refer to the correct pixel location rather than the pixel ID, and then send those coordinates to the hardware, which will then translate those coordinates to a pixel ID based on whatever hardware configuration we've told the board it is running. So it is possible to configure the board and tell it what kind of display it's powering, and the configuration looks like this. So this is code that is running on the microcontroller itself, and it has a single configuration file that includes a bunch of information about what the board is doing. So we have, first of all, a display pin. So on our microcontroller, there's a bunch of different out I/O pins. I'm putting it out of pin number 4 because it's in the top left corner and it's easy to solder. We also have the width and the height of the display so that we can calculate that coordinate and turn it into an address. We have the connector location, so in this case, top left. We tell it what kind of mode of wiring we've got, so snaked vertically, horizontally. And then also this important number here, I learned when I was doing the dress, there's 2 different kinds of addressable RGB LEDs. You can get RGB LEDs and you can get RGBW LEDs, which take an extra number. So they take a white value, which is the brightness. And if you buy from AliExpress 200 individual LEDs, they aren't always the same kind of LEDs, and you wire them all up and you cause yourself a lot of pain and heartache and days of soldering and desoldering. So be very careful, make sure you know whether you've got RGB or RGBW LEDs. If you have W, you're going to have to send an extra color value. But yeah, we can just set it up and tell it which one that we have, and because these LEDs are all bought in a strip, they're all the same kind of LEDs. It's only really problematic if you're buying individual pixels. So when a message arrives at our device, it runs through that initial passing block that interprets the message that the LED driver sent, and then it checks the first byte for the control code, and then it checks the second byte for the control mode, which is an ASCII character, either a P, a T, or an S. So are we sending a pixel? Are we sending some text, or are we sending scrolling text? And the Arduino device driver then needs to be updated to send messages using the correct control mode. So let's have a look at how we would send scrolling text. So that's going to be our S control mode. So the microcontroller software is able to set individual pixels using any size of array, and we have our font sheet stored on the device. The missing piece is to write message handlers that actually process those incoming binary messages, and these are going to look up the font data that's stored in the memory and push the appropriate pixels to the display. Is my mask still going, or has it stopped? Yes, my phone went to sleep. Okay, let's try and wake it up. So when a message to display text is received, the code is going to loop through each of the characters that arrives in that bit between our start of text and end of text and do a lookup for each character in the embedded font. And it's going to get the binary array that we got and the index of each character. And so then what we need to do is decide what location it needs to start drawing at. So if we call that location, for example, the X position, each time a character is drawn on the display, we calculate its width, and then we add one additional space, so the X position is moved along by 1, which is the space in between each letter, and then we draw the next letter, and we update the X position. And as the code loops through, it calculates all of those XY coordinates and is able to draw the characters in sequence. And this continues until the loop reaches the width of the display, and then it's going to stop drawing because those characters are just going to flow off the side. So we can write text to the display now, but there's an extra part that we need to do. We need to scroll that text. And writing scrolling text is actually nice and simple. So it's one subtle change from updating just writing text. So the X position, now we're going to move it across till the right-hand edge of the display. This means that when a message is first received, the X position, so that initial offset that we've got, is equal to the display width, and no pixels will be drawn. We then write a loop that decrements that X position until it equals the total width of all of the characters as a negative number. So if the text string has a total of, say, 100 pixels, we'll keep on drawing and decrementing that X position until the X position equals minus 100, and that'll scroll all the text across the screen. And this is the code for that here. And so if the message mode indicates scrolling text, we start a while loop, which updates the scrolling position in the byte array that represents the entire fonted string. It'll start looping and display a subset of the total data of the string until all of the pixels have been scrolled off screen. And this makes it nice and easy to implement a scroll speed because we just put a time delay in between how often we are scrolling a pixel to the left. Every time this animation is played, the code pauses execution each time it scrolls. And this is super cool. What it means is that the loop that is being done prevents control being returned to the main Arduino loop, which then triggers receiving more messages over MQTT, which means we're not doing more work than we need to. The code on the hardware only ever draws the pixels for the characters that will be visible on the display, which means that we're saving memory by not converting every pixel character ahead of time. It means that we're essentially able to use MQTT itself as a buffer without having to sort of use up memory on the device. Once it's finished scrolling a particular bit of text, it then goes back to MQTT to get any subsequent messages and then starts scrolling that next bit of text, which is just a really nice, efficient way of doing it. And that's it. That is how you build a live captioning mask. And just in case you were wondering, here is me showing my mother the finished result and her looking incredibly bemused and not being quite sure that this was the solution that she actually requires. But she enjoyed that I tried. But there is more. So there's a few parts of the app that I haven't spoken about because we would be here all morning. One of which is, as I mentioned, if you have no display, as I'm sure the majority of you probably don't have one of these in your pocket, no problem. The text will also be displayed inside the app. In fact, the transcription of everything that I have said in this entire talk is now displayed in the app. And so you can visit livecaption.ably.dev, and there's a little share button in there, so I could share my entire talk with you if you wanted to see the text of it live as it's happening in your own browser. And there's also settings in there, as I mentioned, to change the color and the scrolling speed. One of the other things that I've not mentioned is this visual representation of the board in the app. So if you visit livecaption.ably.dev, you can see it. This is an Arduino emulator built in JavaScript that runs the exact same code that is running on the board, but outputs it to divs instead of to lights on an array. Again, this is super useful. If you've ever done any work with hardware, you will know that debugging, especially on a device like this, is really hard. We write a change in the code, we have to compile the code, we then have to push the code to the device. It takes literal minutes. We need to have some sort of debugging, so we open up the serial monitor and see what is going on, and it's just, quite frankly, a pain in the ass. So what we've got here is a visual representation of the array so that we can do testing, and really it was an absolute lifesaver for me. I'm not going to cover it in today's talk because I'm sure you've all had enough of my voice already, but the good news is that if you do want to see it, all of the code is open source and available on GitHub, and you can take it and make it your own if you would like to do so. So you can check it out at github.com/ablylabs, where it is the live caption demo repository. And if you are making other real-time experiences, Ably Labs also has a whole load of other demos that I've built. So if you want to make a chat app, that's in there. If you're making multiplayer games and quizzes, there's some demos in there. Collaborative editing, anything that needs data to be sent in real time, you will find it in that repository there, that collection of repositories. It's all open source. Please do take it and make it your own. As I mentioned, I would really love it if we started seeing more things like this on the market. I am fully aware that this is not the solution to the problem, but it's a start, and I hope that it inspires you to start thinking about ideas like this yourself and how you might be able to adapt it. If you do use any of my projects, do let me know. I love to help out. You can get me at This Is Joe Frank on Twitter, or you can join the Ably Discord where you can chat with me in real time. I'm always happy to help out with any projects that you have. Let me know about it. And if you enjoyed this talk, if you could tweet at Ably Realtime to let my boss know that I'm working, that would be great. But thank you all so much for listening, NDC, and I hope you have a fantastic conference. If you would like to come up and fondle the tech, please do. I've got all sorts of interesting arrays. I've got the array that came in the mask here, which is, you can come and see how beautiful and how bizarre the wiring is on the back. And I have some stickers down there. So thank you all so much.